Hello class, good morning. Today we will conduct an investigation to take some notes, solve some momentum problems. Please get out lab notebook and pen and pencil and open your textbook to page 197, Conservation of Momentum. Pool or billiard is a game of real skill, and it is also a way to look at one of the most powerful laws of physics. We will find out how. In this lesson, we will talk about a few conservation laws, especially for energy, momentum, charge, and mass. These fundamental quantities cannot be created or destroyed. They can only be changed from one form to another or transformed from one object to another. So, what do you think happens to the momentum of two billiard balls of A and B when they strike each other? If you figured that the momentum is conserved, you are right. The law of conservation of momentum says that in a collision between objects in a closed and isolated system, the total momentum of the objects in the system before the collision is equal to the total momentum of the object in the system after the collision. Remember Newton's laws, which predicts the motion of the most objects. His third law of motion states that for every action, any object or at rest will remain at rest unless there is an external unbalanced force that acts on it. There is another law of physics that might sound familiar when we talk about collisions. F equals m times a. An object accelerates in the direction of the net force acting on it. Remember Newton's laws. His third law of motion states that for every action there is an equal and opposite reaction. This means that objects exert equal forces on one another when they interact. One of the consequences of Newton's third law is the law of conservation of momentum. We can see it in action when you hit a straight shot like this and does this. You exert a force on the cue ball which makes it gain momentum. When you strike the ball, the momentum is transferred to it. When the ball collides with the other ball and the first ball stops, all the momentum has been transferred from the first ball to the second ball. But what about in this case? This time the cue ball hits the other ball at an angle and both balls are moving. So, was the momentum conserved? If your answer still is yes, still you are right. Remember that momentum, like velocity and direction, is a vector quantity. When the first ball travels in this direction, it carries some of the momentum with it. The rest is transferred to the second ball, but not enough to reach the pocket. However, none of the momentum was lost, only transferred. Don't forget, only transferred. But objects interact with one another. In our example, ball A and ball B. In equation form, we see that the total momentum P is equal to the total momentum of all the objects after they interact. Here. For an isolated system, the law of conservation of momentum can be stated as follows. The total momentum of all objects interacting with one another remains constant, regardless of nature of the forces between the objects. Now, already to try solving a problem. Ready to try to solve a problem? A pool or billiard player is about to use the cue ball to make a direct hit on a B ball which is at rest. Each ball has mass of 160 grams and the cue ball initial speed is 4.5 per second meters per second. After the collision, the cue ball comes to a stop. If no momentum is lost in the collision, what is the total momentum of this system and how fast is the B ball moving after the collision? Remember, the momentum of an object is equal to its mass times its velocity, P equals to m times v. The unit for momentum is kilogram meters per second. To be consistent, we will convert the mass to the kilograms. The cue ball has a mass of 0.16 kilograms. So let's multiply that by the velocity of 4.5 meters per second. So the momentum of the cue ball before the collision is 0.72 kilograms meters per second. So the momentum of the cue ball before the collision is 0.72 kilograms meter per second. Since the objects at rest do not have momentum, the B ball begins with zero momentum. So the total momentum of the cue ball and the B ball together before the collision is 0.72 kilograms meters per second. And because momentum is conserved, 0.72 kilograms meters per second, also the system's total momentum after the collision is 2. Now, what about the final velocity of the B ball? Since the collision brings the cue ball to rest, the B ball carries all the system's momentum. That means we can divide 0.72 kilograms meters per second by 0.16 kilograms, the B ball's mass, to find its velocity, and that turns to be 4.39 meters per second, the same as the cue ball had at first. See how the law of conservation of momentum helped us to solve this equation. You apply the law of conservation of momentum only when a collision happens in a closed, isolated system. That means matter and energy do not enter or leave the system, which means there are no net outside forces acting on the system. In our example, the two pool balls are the system. They don't enter or leave, so the system is closed. The only forces we consider in this force between the two balls when they collide. We are not concerned about the initial force of the cue stick or friction between the balls and the table. So we say that the system is isolated. Momentum of objects pushing away from each other. Another example. Starting from the rest, two skaters push off against each other on the smooth level of ice, where friction is negligible. When the skaters stand facing each other, both skaters have zero momentum. To the total momentum of both skaters is zero. When the skaters push away from each other, their momentum is equal but opposite. So the total momentum still is zero. We see the conservation of momentum at work all around us. When you step onto a dock from a boat, you push forward and the boat moves backward. When you shoot an arrow at a target, the recoil of the bow has the opposite and equal momentum of the arrow. And when you launch a rocket, the exhaust pushes off forward in equal and opposite measures, sending it out of the Earth's atmosphere with power and precision. Conservation laws, including the conservation of momentum, are vital in physics because they make it possible to predict how a system will behave without having to consider every detail. Once you know a few things about the initial condition, you can say a lot about the final state of a system. So this is our end of this session. I hope you get good notes. And for now, good luck.